What's up, everyone? My name is Dr. Chris Hacks, and today we're back with another CryptoPals Crypto Challenge. Today we're going to be doing the CBC bit flipping attack. So let's jump right in. We're going to generate a random key, combine our padding code and our CBC code to write two functions. So we will append this string and append this string. So this will go to the front, this will go to the back. And yeah, it looks like we're just going to be pretending like we're a website and we have some sort of like cookie or URL or something similar that takes this metadata, and we're going to be breaking it. So this function should quote out the semicolon and the equal sign character, and then should pad the input to the 16-byte AES block length and encrypt it. The second function should decrypt it and look for characters like admin equals true. Okay, we'll do that. We'll probably just look for this to keep it simple, and then return true or false. If you've written the first function properly, it should not be possible to provide user input that will generate the second function, the string the second function is looking for. Okay, so we're gonna basically quote these out, and then we're gonna encrypt it under CBC, and we're gonna find a way to break it. So we won't have the knowledge of the AES key, and we're relying on the fact that there is a 1-bit error. Okay. Alright. And then it does say, before you implement this attack, answer this question. Why does CBC mode have this property? So let's think about this a little bit. Why would CBC mode have this sort of error property? Well, there's a couple of reasons. If we remember back, CBC uses an IV so that every single block affects the block next to it. Okay? So if there's one error in the first block, then the second block will have a similar error because the IV will affect it directly. And because we are XORing the IV with the actual ciphertext blocks, that will also affect it because it will flip it. Hence the name bit flipping. Okay? So modifying a byte in the ciphertext block can corrupt the corresponding decrypted plaintext block due to the way the CBC works. Okay? So we're going to strategically basically do some bit flipping. So let's just get our auxiliary functions completed first. We'll get the encryption and decryption functions completed, and then we can jump into the attack itself. Let's go into here. I already have everything set up. So first things first, let's write our encryption function. So I'm going to do standard string encrypt. Pretty plain and simple. Go ahead and do that. We'll take in some const string reference, call it plaintext, and we're just going to go ahead and encrypt this. So if we go back to the instructions, they want to append certain strings. So we want to append this string. So I'm going to do this, const string prefix equals this, and const string suffix equals the other one. So let me grab the other one. Okay. So those are our two strings we want to append. Put some semicolons at the end. And what we'll be doing is any user input will have this string first and this string second. And we also need to sanitize it. So we do need to sanitize our input. That way the user can't just pass in like, I don't know, semicolon and then like admin equals true, something like that, and then another semicolon. We don't want that, so we got to sanitize it. So we're going to write a sanitize function real quick. So call it sanitize. Call it input because this is going to be some user input. Basically, all we're going to do is we're going to replace, let's just do this. Let's replace the semicolon and the equal sign. We'll replace it with their hex character correspondent. Because like, for example, spaces are replaced here like this with like the 20, okay? Which is the hex character for space. So space is 32 in ASCII, so in hex that would be just 20. So we'll do the same with the equal sign and the semicolon. Those will be special symbols that only our server will be able to add to our encryption. So standard string, let's call it output. And then for each character, for character C in the input, we are going to go if C is equal to the semicolon, or C is equal to the equal sign. Use a switch statement if you really wanted to here, but I'll reserve that for if we had a lot more characters. And then we'll have output plus equals. We'll throw our little percentage sign in front. This is like the encoding symbol. We don't have to worry too much about the percentage sign. You could also add it to this list here if you wanted to. That way percentage signs get encoded, but we don't have to worry about that too much for this proof of concept. Otherwise, in like a real world situation, you might want to, just so that the user doesn't get a messed up string. It won't give them admin access, but it can cause the encoding to get messed up and then cause some issues down the line. But who cares for our purposes? Okay, and then we'll have text to hex. Let me include encoding utils. Coding utils. And then text to hex, and then we'll just put in our character. This might be mad. Okay, it's gonna be mad about that. So we'll just do standard string. Let me stop capitalizing this. String character, and we need one of our character. There we go. So if we like passed in an equal sign, it would take 61, convert that to hex, and then give it back to us. And that's all we have to do to sanitize it. So else, we can just add the character to the output, like so. Well, now that I think about it, yeah, you could also use a switch statement here now that I think about it. Especially if you're going to add more characters to this, might be more efficient, but this should be good enough for our purposes. Alright, we're going to go ahead and return output. Easy peasy. And there's our sanitize function. Now with our sanitize function done, we can do this. Standard string, call it sanitized, equals plain text, or no, I need to call the function. Sanitized, and then plain text. Oh, no D at the end. That's why. Okay. Cool. Once we get that, we can make our encryption string. So if I remember correctly, let me get AES imported because we're going to need our CBC function. Include AES.h. Let's jump into that real quick. We are going to AES.cpp. If I remember correctly, yes, we are padding the data here. So I don't need to pad the data here. It's a little confusing. Our AES functions are a little messy, but we will make do. So I don't need to pad the data. I can just do this. I'll do this. Return AES underscore 128 CBC encrypt, not decrypt. And then what do we need? We need our data, which is going to be prefix plus sanitized plus suffix. You can use a string builder or something else if you want to be a little more efficient about it, but this will work. Okay, and then we also are going to need a key, an IV, and a block size. Okay, so I'm going to do a couple things. Let's do this. First, constant static, or not static, constant standard string. I guess we could make it static, but there's no reason to. Constant string, I'm going to call it key underscore C16, and we're going to need random for this, so include random.h. We're going to do generate random bytes. And then I was thinking about this a little bit. I think we should probably store the key size or the block size. I'm gonna go into AES.8 or not AES.h, AES.cpp. Actually, no, yeah, AES.h might be a little more appropriate. I'm gonna come up in here, const int block size equals 16. I'm just gonna put it in here just so that we have it. I'm gonna call it, actually, let's call it AES underscore block size. Just because we might need to change it later if we're doing other encryption algorithms, which will happen. We're going to be working with other encryption later down the line. So we'll preface this with AES, and then if I need to add like underscore 16 at the end, I can go back and do that later. But this should be good. I'm just going to do this just so we don't have a bunch of 16s everywhere. And then we'll also get an IV as well. That way, we have that for our CBC because we need to pass an IV in. And then, yeah, that should be everything we need if I remember correctly. Okay, so key underscore C16 and IV underscore C16. If we look, it's going to have a constant key and a constant IV, so we don't have to worry about these getting changed. And then our block size will just be AES block size. Perfect. So now we have our encryption function set up. And then if we go back to the instruction, I believe the next thing was the admin function. Yeah, so it should decrypt and look for characters admin equals true. So I'm going to minimize these real quick. Next up, I'm just going to call it bool is admin, and all it will do is it'll take in the ciphertext, the const string ciphertext, and what we'll do is we'll do standard string decrypted equals AES 128 decrypt, and we'll pass in our ciphertext, our key, our IV, and our block size. And then all we need to do is return if we can find the string or not. So return decrypted dot find, and we're looking for where was it? Admin equals true. This is what we're looking for. I'm gonna call it target. Const standard string target equals this. We're gonna do find target, and then if it's not equal to string no position. And if this is the case, that means we found it. That means our attack was successful. We return true. All right, seems like all of our auxiliary functions are set up, so now we can actually focus on the attack. So what we're going to do for the attack is we're going to have a little bit of offsetting. So there's a couple ways to do this. If we remember back to our ECB functions, we were going through and we were calculating out things. So we were going in and checking, okay, how long is the prefix? How long is the suffix? Because if we remember back, we had to basically find the target with the prefix. We had to find the prefix length. So we know how to do that. We can do the same thing in challenge 16. If you guys want to implement that, feel free to. However, for the sake of simplicity, I'm just going to go ahead and assume we already know it, because we do. But like I said, if y'all want to be very methodical about it and do it the right way, then you can go ahead and calculate out the length of the prefix, calculate the length of the suffix. And if you guys need a video on this, I can go over it. We can have a little follow-up video to this challenge. But for now, we're just going to go ahead and we're going to say we already know it. So what I'll do is this. Int prefix length is going to be, I believe it's, let's see, 32, because 33 minus the null char, so 32. So we already know that. Okay? And that means our we can skip those 32 bits, and that's also 2 blocks worth, so that lines up perfectly. In real life, we might have to do it the challenge 14 way, but for now we'll keep it simple and just get the bit flipping proof of concept up and running. So, what we're trying to get is we're trying to do standard string. I'm going to create a target, and our target string is just going to be this admin equals true. That's what we're looking for. That's what we're trying to insert into our ciphertext. Okay? So what I'll do is basically we're gonna craft a an input to do a couple of things. So if we craft our input correctly, we can like go ahead and flip the bits of what we're trying to have basically encrypted out or sanitized out. So here, let me just check my notes real quick. What we'll end up doing is insert a controlled input, okay? And then we find the target block we're looking for, which will be this user data block. We already know this is going to be 2 block lengths, so it'll be easy to find. And then we're going to slightly modify it so that when it gets decrypted, it produces a string. Okay. Let's just jump into the code. Let's just get started. Basically, we're going to create this crafted input here. So standard string. It's going to be a string of target.size. So our target is 13. Or I guess if you ignore the null, it would be 12. So target.size. And then we'll have just like a placeholder. So we'll use A as a placeholder. Okay. And then we can encrypt this. Like so. Okay. Now what we can do, right, we can go in and flip the encryption that we just got. So what we will do is we're going to take each one of these characters and XOR it with this crafted input after it's encrypted. And that bit flipping attack will work. Now the reason why this works is a little bit complicated, but it has to do with how the XORing logic works. So like when we have CBC mode, we'll just go over this real quick. Our ciphertext is going to be basically our encryption, which will be our plain text block XORed with our previous ciphertext block. And if we remember, our decryption is just going to be the plain text is equal to the decryption formula of the ciphertext block XORed with the previous ciphertext block. So when we go ahead and do this, we're going to end up with our original plaintext XORed with our original ciphertext. However, we also get this XOR for our desired flip. And because of that desired flip XOR, we're able to get this target inputted in. We're able to get it thrown into the mix. Okay? So let me show you what I mean by that. Once we have this encrypted output, we have our ciphertext. We can go ahead and for int I equals 0, I'm going to iterate over this real quick. I is less than our target.size, then I plus plus. Encrypted is just going to be our prefix length which we already know is 32, minus our block size, which we know will be the AES block size, times plus I. Hold on, let me make sure I do this math right. All right. Okay, so we're basically going to mess up the block right before our crafted input. We're going to XOR it with our target so that our crafted input will be XORed back correctly. So I'll show you guys what it looks like at the end, because our input, this block right here, is going to be real messed up. But our target block is not going to get messed up. It's going to be outputted correctly. So if I go ahead and do this, encrypted of this character is going to be XORed with our original character, which is A, which is going to also be XORed with our target character Y, like so. So the block before our target will be messed up, and then our target will be able to be output correctly. And this only works if you do have a prefix. If you don't have a prefix, then you won't have a block beforehand to mess up, and it won't work too well. So you might have to generate your own block. You might have to generate your own 16 characters of information so that you can get this to work. All right, and then we can just return encrypted. Or I'm sorry, that's not right. We now have encrypted all ready to be used. Okay. So once encrypted is all ready, I guess I could probably throw this into its own function, potentially. Yeah, I'm gonna go ahead and I'm actually gonna throw this into its own like attack function. So standard string, we're gonna call it bit flip attack. Taking a const string, so I'll call it cipher text. Are we gonna need it? Will we need to take in a string? I don't think we will actually. I don't think we're gonna need to take anything in. Thinking about it, because we are modifying everything here, like so. Then return encrypted. I believe that's all we need to do. Just package it up all nice and neat. Yeah. Yeah, because we're not going to have any, because this will just generate what we need. Okay. So... yeah, this should work. This should work. Okay. All right. So what we'll do is we'll make this look all nice and neat. So let's just get some placeholder input just so we can show what the encryption looks like. So standard string, I'll just do placeholder, and then we're just going to pass in AES underscore block size. I'll just put in a bunch of A's. Now, what I'm doing here is I'm just going to make it look nice and neat. So that our output, when we're done with challenge 16, looks nice. So let's get a result so that we can output everything at the end. And we'll return results so that when we actually run it, we can see some stuff. Just because if we don't do this, then everything's going to be running in the background and we won't be able to see what's actually going on. Or any sort of output. Alright, so we'll just get result is just going to be this. So we'll call it like this. So I'll call it original. Or I'll call it normal encryption. Actually, I'm going to put a new line at the beginning so that looks all nice. Normal encryption plus, let's do this, text to hex so that it doesn't get all messed up. and we will encrypt our placeholder. And then we can add a new line at the end as well. All right, cool. So that will give us a example of what the encryption will look like. You can pass in some other stuff. You can test out the sanitization function by passing in some things. Like if I passed in admin equals true, let's actually just do that. Let's just do this, so that we can show that this will not work, because we're not able to, they'll get sanitized out. So I'll just do that just to prove it doesn't work. And then we'll just do this. Result plus equals has admin equals, and then we'll do this plus, and then we can do an inline if. So we'll do oh, I guess I need to hold on to the encryption. So standard string, call this, like, I guess naive. That way we can just like ensure that it doesn't actually work. We can't just pass in our string that we want. So we'll do this, put this back in here, text to hex, naive encrypt, has admin will be plus, believe we called it, oh yeah, we gotta do this. Has admin, or what did I call it? We called it is admin. And we'll pass in our naive encrypt. Okay, and then what we can do is question mark, and then we can do true or false. Cool. Okay, perfect. I'll call this is so that it matches our function. All right, so now we'll basically show that the naive way of encrypting things doesn't work because it gets sanitized, and then we can do our little bit flip attack. So I'll call this standard string bit flip encrypt, and that will just be the function from earlier. So bit flip attack. I guess we could theoretically pass a target into this, and then instead of declaring it, that might be a good way of doing it as well, but we don't need to do anything. All right, so bit flip attack will return the encrypted with our bits flipped, and then let me do this, and then I'll do this. Result plus equal, and we'll do bit flip encryption will look like this. We'll take this here and paste it in here. And then is admin will just be bit flip encrypt, and then it'll be true or false. And then also I will decrypt the final result just because, yeah, wait, hold on, let me make sure this works. Yeah, so that'll have an extra new line we don't need. Or I guess, actually, no, we will need that, huh? I could add it to the end of here, but okay. Yeah. And then I guess I should include this as well. Result plus equals, and then we'll have another new line, and we'll put decrypted text, just so that we can see the first block getting all messed up. And then it'll just be plus AES underscore ECB underscore, or no, not ECB, CBC. 128 CBC decrypt, and I'll pass in our bit flip encrypt, followed by our key and our IV and our AES block size. Normally we won't have access to that function. I just want to demonstrate what it will look like after it is decrypted so that we can all see. But I'll do this, and then I'll include a new line at the end. And that should be it. That should be it. If we go ahead and run this now, we should see that the first naive encryption doesn't work at all. And our second bitflip encryption does. And I guess I probably should include build errors. All right, I'll take a look at that in a second. I should probably include this here just for showing it off, like showing the difference. So naive, encrypt like that. There we go. All right, let's see. What are the build errors? It is mad about result defined in multiple places. Oh, duh. Don't need this again. Yeah, I gotta be careful with that. Yeah, I think that should be good. That should make it look all nice and pretty when it gets output, so that we can see the attack in action. But yeah, this just goes to show CBC's downfalls. Okay, so here it is. Has admin equals true. This should not be true. Actually, I guess my has admin function is incorrect, because this is incorrect. This is just straight up incorrect, because this one has the target string we're looking for. So the second one's correct. Like, as we can see, you know, comment and this is all, hold on, I probably passed in the wrong thing. Did I? No, I passed in naive encryption. Yeah, because I mean, technically this does not have admin, because this does not count. That's not what we're looking for. It does not count. This, on the other hand, does count. That is what we are looking for. We are looking for has admin like that. It does mess up the first string, so we might need to pad a little bit more so that it doesn't get super messed up. That way we can still see it. So I'm going to go ahead and do that real quick. I'm actually going to include an extra block size. And let's see what happens. Let's see what happens. Let me run this again. That way the first, that block of A's gets messed up. Yeah, so true. Wait, did I include it at the wrong spot? I did. I need to actually get rid of this. Like so. That's what I did wrong. Okay. With that, now we'll pass in a bunch of A's that will be random, and those will get messed up. Yes. So if we look here, those A's will get messed up. Now for this one, let me do a little bit of debugging. Let me figure out what's going on with this, because this should be false. So I'll be back in a sec with the answer. Alright, so apparently the compiler didn't like when I had is admin and then another like if statement here. So I went ahead and got rid of that. I moved it to a new line so that it was a little bit better, and it ended up working. I'm assuming I had some weird syntax I was messed up with. But also, I'm going to include print utils for utils.h. That way we can format as printable, because we should probably go ahead and make this printable. And yeah, I realize we do not need it to have a prefix necessarily. I just added a block size worth of A's, and then I'm corrupting those A's instead. That way the actual output looks a bit better. It won't mess up any of the metadata that the server would be encoding on. Because yeah, like as you can see, user data equals all this random junk, and then it's just like the server would hopefully ignore something like that, and then we have admin equals true. And then there's another semicolon, so it would probably just filter that out. But yeah, that's all we needed. That was the whole attack, and we can see that we can actually corrupt the block before the block we're worried about, and flip some bits because of how the IV works, which is why this encryption algorithm is not used anymore, because it's so easy to break. But yeah, hopefully y'all learned something. We got to do some very, very nice decrypting and some code breaking. So Thank you all for watching. Make sure to tune in for the next video. And we just finished set 2. So good job to everyone who stuck around. We got through 2 full sets. We only have, what is it? Let's take a look here. We have a total of 6 left. So we're making some good progress. So thank you all for sticking around this whole time. And I appreciate all you watching. And see y'all in the next video.